this lesson shows you why, one of the reasons why we look at the second derivative of a function with respect to x. If we differentiate once, then we can find the stationary points. That is, when the gradient is equal to 0. Now, if we find the second derivative and find that for a given x coordinate, which we know to be a stationary point, then if we put that coordinate in the second derivative and it works out to be bigger than 0, then the stationary point will be a minimum. However, if we find that it's below 0, then it will be a maximum. If it is equal to 0, then arguably it could be either of these two, or it could be, and most likely is, a point of inflection. Now, whilst you're learning about the quadratic curve at GCSE, teacher would have always told you that if it involves an x squared, then the graph is always like that. And if it involves a minus x squared, then the graph is always that way around. That is because, as I've written up here, that the quadratic, the second derivative, will always tell you what it is. So dy by dx is equal to 2x take 2. To find the stationary point, we put that equal to 0. Now if I take the 2 across, 2x is equal to 2, so x is equal to 1. If I work out the second derivative, differentiation of 2x is 2, differentiation of 2 is nothing. Now 2 is bigger than 0, therefore we've got a minimum at 1 comma, and if I put 1 into here, the original, we get 1 squared, which is 1, take 2 ones, which is 2, take 1, so we get minus 2, minimum point. However, when you've got a cubic, you have to do some work down here. So differentiation of that, we have that dy by dx is equal to 3 take 3x squared. If I put that equal to 0, then 3 take 3x squared equal to nothing means that x squared will equal 1. So therefore x can be 1, but also x could be minus 1. So we have two stationary points. Well, if I differentiate again, that goes to nothing. Differentiation of that is minus 6x. Now if I start with 1, so when x equals 1, the second derivative works out to be, put 1 into there, minus 6. So therefore that's below 0, therefore we've got a maximum when x equals 1. If I put minus 1 in, then minus 1 into there makes that positive 6, which is above 0. Therefore, we've got a minimum when x equals minus 1. And if I put the 1 into there, find the y coordinate. If I put minus 1 into there, find the minus y coordinate. Okay, so for many years this has been a typical A-level question. So to find the stationary points, just like with the previous two examples, we work out dy by dx. So differentiation of that is 3x squared. Differentiation of that is minus 6x. Differentiation of that is minus 9. Whilst we're at it, we may as well do the second derivative because we know we're going to have to use that at some point. Differentiation of that is 6x. Differentiation of that is minus 6. So, to find the stationary points, we need to put that equal to 0. We need to do 3x squared minus 6x minus 9 equal to 0. Now I can make the problem a little easier because I can divide everything by 3. 3 is a factor of every number there, and therefore it makes it easier to factorise. X and x for x squared, 3 can only be done by 1 times 3, and I can get the minus 2x if I make that a minus and make that a plus. So therefore we have that x is equal to minus 1 and we have that x is equal to 3. Now at the same time we can work out the y coordinate, which is easier and quicker to do from the calculator. So if I put minus 1 into x cubed minus 3x squared and minus 9x and plus 2, out comes 7. If I do the same with 3, so I put 3 into the calculator, that comes out as minus 25. So next thing, with them two corners worked out, we need to put in minus 1 into the second derivative. So when x equals minus 1, we have that the second derivative works out to be minus 6 minus 12, which is below 0. So therefore we have a maximum at minus 1,7. Whereas when I put x equal to 1, then the second derivative works out to be, 3, not 1. 18 takes 6, which is 12, and that is bigger than 0, so therefore we've got a minimum at 3, minus 25. So this next one's very similar to that previous one, with the exception that we're going to draw a sketch of the graph based on what we find. So I start off for the stationary points doing as I did before. I differentiate 6x squared minus 12x, nothing, and I differentiate again. 12x, 12. I then put this equal to 0 to find the stationary points, so 6x squared minus 12x equal to 0. I can take a 6 and an x outside of a bracket here, leaves an x for x squared and a minus 2 for the 12x. So that means that x equals 0 is one solution, x equals 2 is another one. Now if I put nothing into there, it's easy enough, I get 12. If I put 2 into there, again, let the calculator do the work. So we've got 2 lots of 2 cubed, take 6 lots of 2 squared, plus 12, and that comes out to be 4. As before, we would then put nothing into here. So x equals nothing, then the second derivative works out to be nothing minus 12, so minus 12, which is below 0. So therefore we have a maximum at nothing, 12. Repeat the same maths with the 2. So put 2 into there, you get 24. Take 12 is 12. You tend to find that these are the same but opposite signs. Not always, but more often than not. Anyway, that's greater than 0, so therefore we've got a minimum at 2,4. So they are our 2 points, and from that we can then move on to part B and sketch the graph. Now to sketch the graph, all you would do, no graph paper required for sketching the graphs, you draw an XY axis, at nothing, we're up at 12, and we know that that's a maximum, so we know that that goes like that way around. At 2, we're up at 4, know that that goes that way around. So therefore the graph must come up to the 12, turn round, come down to the 2 there, and back up. That is actually called a local maximum, and that is called a local minimum, because clearly that's not the maximum value, it goes higher up here, and that's not the minimum because it does go lower here. But that's a sketch using those 2 coordinates that we found in part A. Now to answer part C, it says how many roots are there, how many real roots are there for the equation equal to nothing? Well, it's equal to nothing on that line, and you can see there's only 1 root. Question finished. So over the years, the cubic has been a popular one for stationary points at A level. However, they can ask whatever they like. So here's one where we've got a quoting. So same thing, we would differentiate, and we get 12x cubed minus 24x squared and plus 12x. And then if we differentiate again, we get 36x squared, 48, he says, 48x and 12. So in order to find the stationary points, we need to put the first derivative equal to 0. Now again, I can make life easier by dividing everything by 12 here. So we get x cubed, 2x squared, 1x and nothing. The letter x can come outside. And that factorises to that or bracket squared. So we've got 2 values, x equals nothing, and we've got x equals 1. When I put x equal to nothing, I get y equal to nothing. And when I put x equal to 1, I get x equal to, well, 3 minus 8 plus the 6, so that is 1. Now if I put nothing into there, x equals nothing into the second derivative, I come out with nothing, nothing, 12, which is bigger than 0, so therefore we've got a minimum at nothing comma nothing. And when I put 1 into here, I get 36, take 48, plus 12, I get nothing. Hence, the reason I didn't write it down, I have to do additional work. So, what I would do instead is I'd look at the change of gradient. So we just make some space. We know that at 1, 1, when x equals 1, the gradient is nothing. So I look at a value just before 1. Now I can't look at 0 because 0 was one of the stationary points. So I'd look at 0.5, and I'd look at a number bigger than 1, so 2 for example. And then what I'd do is I'd put these values into the gradient to see whether it's a positive gradient or a negative gradient. So if I start off with the 0.5, what I'm going to do is 12 lots of 0.5 cubed, take 24 lots of 0.5 squared, plus 12 lots of 0.5, and that comes out as 1.5. Now I'm not bothered about the number, just the fact that it was positive. Now if I do the same for 2, so if I put 2 into that setup, I come out with 24, which is also a positive gradient. So we know that at 1 the gradient is nothing, but we know that before 1 the gradient was a positive gradient. We know that after 1 the gradient is a positive gradient. So we know we know, we just do it here. Positive gradient, we've got a point of inflection. Now if I put the two results together, it ain't asked, but I will draw it, the graph, then what we have at 0, 0, we know that it goes like that. And then at 1, 1, if I exaggerate 1, 1, we know that it goes like that. Positive gradient, 0 gradient, positive gradient. So the graph must have come down here, turned round, levelled off, and then gone back up. Minimum point, point of inflection. And that's the graph for that equation.